Mr. Drover here. If you forgot my pretty face, here it is. And today we are doing our first video lecture. Today we are learning about moles, molar mass, significant figures, and scientific notation. Now, these are probably the most important things when transitioning from chemistry to physics. So we got to go through it today. I'm going to try to make this as amazingly entertaining as possible, and hope that you follow along, you take notes as we go. And that's just to ensure if you're confused on the way that I explain, you can look at other videos and that could probably help you out a bit more. But without further ado, let's jump right into the lesson. Now the first thing we have to do is define what a mole is. A mole is just a made up unit. It's like a Stanley nickel or a Schrute buck or a Drover dollar, right? When we're looking at an atom, well, we can't even see an atom, but when we're discussing an atom, it is so tiny, so small that it's hard to measure. Okay, just one atom is very hard to measure because it is so light. So the mole is a concept that is used so that we can actually measure the mass of elements and compounds, all right? It's just a number. It's, again, Stanley nickels, Drover dollars. 1 mole is actually equal to 6.022 times 10 to the power of 23 atoms. 1 mole represents 6.022 times 10 to the power of 3 number of atoms. How many atoms is that, you ask? Good question. 602 hexillion atoms. Now that we know what a mole is, we're going to talk about molar mass of a substance, all right? So the molar mass is measured in grams per moles. The atomic molar mass are given on the periodic table. So the atomic mass is actually called the atomic molar mass. It's the same thing. It's synonymous, all right? Think back to the start of the class when we talked about the periodic table and what all those numbers meant on it. We talked about the atomic mass number. This is actually the same thing as the molar mass. So when we refer to atomic mass, we're talking about the atomic molar mass. For sodium, 1 molecule of sodium is 22.99 grams per mole. So what that means is that sodium weighs 22.99 grams per 602 hexillion atoms. So now let's look at our boy oxygen. Now we know oxygen doesn't like to be alone. He is super, I don't know, there's a phobia when you're alone. So he likes to hang around like-minded people. So he always hangs out with at least one other oxygen if no one else is around. This is called diatomic. So remember, oxygen is diatomic. When it's by itself, it has to have at least 2 of them. Okay, so it's always O2 in nature. The atomic mass of oxygen, just 1, so monoatomic, which is not found in nature, is 16, all right? So O2 has a molar mass of 2 times 16 grams per mole. So in reality, 602 hexillion atoms of O2 weighs 32 grams. Is that making sense? So if you have sodium, just raw sodium, okay, and you put it on a scale and you weighed out 22.99 grams of sodium, you're actually looking at 602 hexillion atoms. That's a lot. Imagine. Now think about how small the atoms are to have 602 hexillion atoms in 22 grams of sodium. That's crazy. That's crazy! Alright, so since compounds are made up of a bunch of different elements and that we know each element has a different molar mass, okay, then we have to learn how to calculate mass of compounds altogether. Molecular or ionic, doesn't matter. The formula we're going to use is M equals N M, okay? So M equals N capital M. The lowercase m equals mass, the N represents moles, and the capital M is the molar mass, okay? So you multiply the number of moles by the molar mass to get the mass. Don't know what that was. So let's look at this example here for sodium chloride. Now this sodium chloride is table salt. Yo, so I was walking down the street and someone threw sodium chloride at me. Whoa, dude, that's assault. Taking a look at sodium chloride, the mass of 3.00 moles of sodium chloride. So what we do here is we follow that formula, okay? So M, capital M, capital M is the molar mass. So the molar mass of sodium, so just sodium, is 22.99. We should know this by now, okay? And then the molar mass of chloride is 35.45. The molar mass of chloride is 35.45. So what that means is that you have to add those up, okay? So you add 22.99 plus 35.45, and then you get the molar mass of sodium chloride, which is 58.44 grams per mole. So 602 hexillion atoms of sodium chloride weighs 58.44 grams. That's crazy. That's crazy! So to calculate the mass of 3 moles of sodium chloride, you would simply multiply the molar mass of sodium chloride by 3. Okay? So if 1 mole of sodium chloride equals 58.44, then what you have to do is multiply it by 3 to get the mass of 3 moles. Okay, so 3 times 58.44 is 175.32. So now we want to try to rearrange the equation so we can find all the different variables, like many 3-variable equations. So we have capital M, which is the molar mass, so the mass, okay, and then we have N, which is the number of moles, and then lowercase m, that's just the mass, not the molar mass. So to find the mass of a compound, you would go N times M, all right? The number of moles times the molar mass, okay? To find the number of moles, you go to total mass divided by the molar mass. So if we were to calculate the moles of 24.5 grams of K2O, we'd have to figure out the molar mass of everything here. So the molar mass of potassium is 39.1 grams per mole. So 602 hexillion atoms of potassium weighs 39.1 grams. You times that by 2 because K2O has 2 potassiums in it. So that would be 78.2. Next, you want to grab the singular oxygen molecule attached to it. Now, one molecule of just oxygen weighs 16 grams per mole. So we go 78.2 plus 16. So the total molar mass of K2O is 94.2 grams per mole. Now, if we wanted to find how much moles are in 24.5 grams of K2O, we would simply divide the mass of the compound altogether and divide it by, we would simply grab the mass of the compound altogether, so that's 24.5 grams, and divide it by the molar mass, so that's 94.2. So if you go 24.5 divided by 94.2, so we find that 24.5 grams of K2O actually consists of 0.26. Alright everyone, so we're going to start with significant digits here. And this is going to be a little hard to get used to for some of you because it's a little different than math, okay? So in physics, when completing calculation questions, you need to accurately round your answer based on the numbers given in the question. That's different than math when you have to round your answer to, let's say, like the nearest tenth, okay? Okay, here's an example. So 100 divided by 15. Now, if you type that into your calculator, you would get 6.666 repeating, and then eventually you'd be told to round it to 6.7. Now, in science, so chemistry and physics, it's a little different because you have to follow a bunch of different rules, okay? When deciding how many digits to round your answer to, it's based on the number of significant digits in the numbers given in the question and the mathematical operations you are performing. So there's certain rules that dictate what numbers are significant and what numbers are not significant, and we are going to go over them. So here is the first set of rules. This is when you're just looking at a number. We're not talking about any calculations yet, just what is significant in these numbers. First of all, any digit that is 1 to 9 is significant. So any digit from 1 to 9 is significant, and then trailing zeros are also significant. So what are trailing zeros? Trailing zeros are the zeros at the end of a number. So if you look at the first example here, 6.3800 or 12,000, they both have 5 significant digits because any digit from 1 to 9 is significant. 6, 3, 8, those are all significant. And then the zeros, since they're trailing zeros, they're also significant. So all the digits count here. All right, another rule here is about the sandwich zeros. So think about sandwich. The zeros are the meat, okay? So any zero that's between two numbers is considered significant. So in these two examples, 2.04, the 0 is significant as well as the 2 and as well as the 4 because those are all digits that between 1 and 9 or they're a sandwich 0. So 2.04 has 3 significant figures. The next one is 1005.002. All digits count here too. Why? Well, let's take a look at it. So any digit from 1 to 9 is significant. So the 1, the 5, and the 2 are significant. The trailing zeros, there's no trailing zeros. But the sandwich zeros are also significant. So the zeros between the 1 and the 5 are significant. And the zeros between the decimal and the 2 are also significant. So all 7 digits here are significant. All right? All right, and here's the plot twist. Leading zeros are not significant. All right? So in this example, we have 0.0065. Now, a leading zero is a zero without a significant digit ahead of it. Okay? So in this case, even though we have 0.0065, only the 6-5 are counted as being significant. The other digits, like the leading zeros, do not count. Okay, so there's 2 significant digits in this example. So now we know how to determine what numbers are significant and what numbers aren't significant. But now we're going to have to throw that rule into some of the operations we do. So there are different rules for when you multiply and divide, and there are different rules for when you add and subtract using significant digits. So let's start off with the multiplying and dividing rules. So for multiplying and dividing, the rule is that you round to the lowest total number of significant digits in the equation. So for example, you are given 2.00 times 20.00. The first thing you have to do is determine what numbers are significant in this equation. So 1 to 9 are always significant. So 2 and 2 are both significant. Trailing zeros are always significant. So we look at this and we go 2.00. How many significant figures in there? 3. Then we look at the next number, 20. 20.00. They're all trailing zeros, and the 2 is between 1 and 9. So there's 4 significant figures in there. So that means that the answer to that equation is going to be 3 significant digits. So you're going to round it to 3 significant digits, which is 40.0. So 40.0. All right? So now let's go over the rule for adding and subtracting using significant digits. This one is a little bit more straightforward, and that the rule is that if you are given a set of numbers with different decimal places, you round your answer to whatever the lowest decimal place in the equation is. So, for example, you have 5.2 plus 2.35. Okay? Your final answer would round down to the lowest decimal place in that equation. So in this instance, it's the first decimal place because of the 5.2. All right? So your answer would be 7.55, but if you're using significant digits, you would round it to 7.6 because you're rounding up. But you only round to one decimal place because the lowest decimal in the equation is one decimal. Now, if it was something like 5.22 plus 2.35, then yes, you would keep it at 7.55. All right, so now we're getting into scientific notation, and this is important because sometimes your answer is going to come out with more significant digits than you're allowed to keep. So we'll do this example together here. So you did an equation, whatever it was, and your answer was 5,655. For whatever reason, due to the rules that we talked about before, you can only answer up to two significant digits. Now, 5,655 has at least 4 significant digits. So what we need to do is cut that down. So what you do here is you want to move the decimal place of your answer so it forms a number between 1 and 10. So in this instance, we move it 3 decimal places. So we move it to right after the 5 in our answer. So that equals 5.655, which is in between 1 and 10. Now, if I were to write this 5.655 to the power of 10 something, we're still going to have 4 sig figs, okay? So what we need to do is we need to round our original answer normally to 5.7. 5.655, we're going to turn that to 5.7, and then we're going to put it 10 to the power of something. Now, how do we discern what power to put in our scientific notation? Well, it is actually the number of decimal places that you moved to get your original answer to be between 1 and 10. Alright, so that is all for today's lesson. I know I went through a bunch of it a little bit fast, but don't worry, a lot of this stuff just takes practice. So I will link a couple of videos that also explain the same thing as what I just explained about scientific notation. Your assignment is also going to give you a lot of practice on how to write scientific notation. So if you have any questions at all about any of the topics we covered, including scientific notation, because I know it can be a little confusing at times, please write your question on the stream on the Google Classroom. Then myself and others can look at it and we can all help each other out. Okay? Also, please watch a couple other videos that I'll link. It's with other people that explain the same stuff, and you might get more out of that depending on what way you learn. Okay? If you're having trouble, please read the textbook if you have it. That helps a lot too. And then we could all figure this out together. All right. So that is everything for this week. Please do the assignment I handed out on Google Classroom, and everyone stay safe. All right. See ya. Oh, what's a good joke? Yo, why doesn't the rap game trust Eminem? Because he's a mole. What makes you say that? Because M-N-M.